First of all, thank you to Tecnológico in Monterrey for inviting me and giving me the opportunity of being here. Thank you to Professor Elias, Dr. Alvera, and the whole University of Tecnológico of Monterrey. My name is Aitzol Lamikitz, and I will present the case study of the CFAA. CFAA is the acronym of Centro de Fabricación Avanzada en Aeronáutica, Advanced Manufacturing Center for Aeronautics, which is located in the Basque Country, and we are working on metal additive manufacturing for aerospace applications. So just a brief presentation. I come from the Basque Country. The Basque Country is in the north of Spain, so very close to France. Main cities are Bilbao and San Sebastian. Probably you know Guggenheim Museum, La Playa La Concha or San Sebastian. And this is my university. The University of the Basque Country is the public university in the Basque Country. And we have a faculty of engineering in the city of Bilbao, which is the most industrial city. And basically we have machine tool builders and aerospace, some automotive tier 2, tier 1 level, and some equipment of, I will say, heavy metal industry. So this is the research center, the CFAA. It's located about 12 kilometers. The idea is to work on mid-high tier levels to the industry. We have now more than 100 partners, companies, and the idea is to work with real machines, big machines, in order to get the results directly to the industry, not to scale up from the lab to the industry, and try to jump basic research to the industry rapidly. So here projects usually are measured in weeks, and probably it's better to see a video. I don't know if, please, I don't know if, can you activate the video? It's not automatic. And I don't know, is it possible to activate the video? Okay. So, this is the center.
Es el Centro de Fabricación Avanzada Aeronáutico. Lo que buscamos es una investigación tecnológica muy cercana a la necesidad de las empresas y transmitir los resultados en muy corto espacio de tiempo.
Los proyectos que se realizan en el CFA son muy finalistas y tienen niveles de TRL entre 6 y 7. Esto significa que tenemos que utilizar unas máquinas similares a las reales para que se puedan emplear los resultados directamente.
So you see, we have machining, welding, metrology, X-ray, CT, and also metal additive manufacturing. So basically, in metal additive manufacturing, we have 2 laser deposition systems and 2 powder bed machines, powder bed fusion machines from Renishow, and also software monitoring. And the idea is to tackle the project in these mid-high tier levels. So going to the context of the aerospace industry, probably you know that there are a lot of forecasts, different numbers, but the same conclusion for all of them. The demand on the next 20 years for aerospace industry will be huge. Some forecast points that more than 40,000 planes are needed in the next 20 years to replace and grow the fleet, mostly in single aisle. Medium planes, 737, A320, but 20% of wide body. So the scenario today now is that the need is to deliver. So the manufacturing processes have to implement new methodologies in order to deliver this high demand. And also, here I say short, mid-term, but I should say now also the efficiency and reduction of noise of engine is also a driver. So the manufacturing processes have to tackle this challenge also. And then in future, in long term, the future will be zero emissions with hydrogen engines, maybe electric for small planes, let's see. But now our trend is to develop manufacturing processes to deliver an efficiency. So just to give you a short example, in short, aircraft engines are becoming more complex. The trend is to increase efficiency, and to increase efficiency, there are only two ways: increase the temperature and increase the pressure. So increase the temperature deals with new alloys, and increase the pressure means more speed in the compressor, in the turbine. So we need gear turbofans, multiple axes. So since the engines are becoming more complex, the role of additive manufacturing here is very relevant, since, as probably you know, and yesterday we talked about it, in additive manufacturing we have complexity, we have tailored parts, and aerospace parts are in that area, so are quite complex, and not so much identical parts. We are talking about thousands of parts per year. So additive manufacturing play a very relevant role here. So basically, in aerospace, we are dealing with two different processes. I will go also fast with that, because yesterday we talked about it. The powder bed processes and the direct energy deposition. Powder bed processes mainly applied for manufacturing small, medium parts from scratch, and direct energy deposition for deposition of material onto a previously forged or cast part for repair or coating. So going to the first example, powder bed processes can be divided also in two different branches. So yesterday G talked about it. So we have binder jetting, where we use a binder to obtain a green part, and then we go to sintering. And this process is being now evaluated by the aerospace industry for non-weldable alloys, but it's still ongoing. So the main process in aerospace is the powder bed fusion, where we use a laser and electron beam to melt powder and obtain a virtually 100% dense part. And it's probably the most implemented technique in aerospace by now. And just to give you an example, those are the facilities of GE Avio in Cameri in Italy, and they have more than 50 machines of EV, and they are making the part that yesterday in the talk of GE you could see is the first rotary certified part in aerospace, blade of gamma TL alloy, titanium aluminum. So going to the second group of processes, the direct energy deposition. In that case, we use a laser or an electric arc to deposit material. In that case, the deposition rate is much higher. Also, the resolution is lower, the precision is lower. And here, mainly these techniques are used for repair, for coating, and even make bigger parts. And I show you now an example. This is an example of Norsk Titanium, a Norway company. This is a titanium part made by wire arc additive manufacturing, and it's a structural part already flying, already certified. And all other examples, this is in our case for our lab, a hybridization between forging, the substrate is forged, and then we deposit this structure in order to reduce the volume of material, to increase the efficiency in terms of material, and reduce the buy-to-flake ratio. So we buy less material in order to increase the efficiency. So, okay, going to the second part of my presentation, which is the main challenge. The main challenge for additive manufacturing by now is the quality and reliability for aerospace industry, I mean. Why? Because additive manufacturing process robustness deals with different processes, different disciplines. We have material, we have software, we have different parameters in the machine, we have lasers, we have wire arcs. So it's very difficult to establish a standardization and a certification, and by now the processes are being certified one by one, and not the processes but the parts are certifying one by one. There is a lack of process repeatability by now. We do not have history. Machine parts are being certified from the 60s, and additive manufacturing is 10, 15 years old, so it's very young. On the other hand, we have lack of data of materials. A lot of material properties are owned by the OEM, so there are not catalogs, nor data sheets of materials. It's quite difficult to find parameters. It's very difficult to find methods and standard testing methods. It's true that ISO is developing new standards, but they are ongoing now. So we have also the processes that make an the parts are with some anisotropy, which makes it more difficult in order to obtain the properties. The designers also doesn't know how to deal with that. So in conclusion, there are many showcases. You can find a lot of parts of additive manufacturing in the websites and in the fairs, and a lot of examples for showing, but not so many real cases flying actually. Okay. In short, metal additive manufacturing is still under consideration by the industry, and particularly by the aerospace industry. And one of the most relevant barriers for these processes are the lack of general compliances and certification requirements. And this is my opinion. The word print is, for me, is the worst enemy, because people think that just giving the green button, the part will be right, and this is not true. The truth is that we have raw material validation, software, process parameters, part separation, and post-processing, heat treatment, and finally the post-process. And each of the steps need a specific validation, so we have to make a powder reception, simulation software. This is still ongoing. Monitoring and data processing also is ongoing, so everything is to do for the quality assurance. Okay, so just to finish my presentation, I will try to present you two case studies, two real projects that are ongoing in our research center, one for laser powder bed fusion, another for direct energy deposition. So in the first case, we have the laser powder bed fusion processes monitoring, and the basis are, the hypothesis is that laser powder bed fusion process, if we do it right with the good parameters, with the good materials, we obtain good parts with no defects, as you can see in the center of the slide. But if we drop a little bit the energy density, or if we go higher with the energy density of the laser, we obtain porosity in terms of lack of fusion or gas porosity. So we need to know if we have a good or bad part. Which is the bad news? The bad news is that currently there are no industrial non-destructive techniques that are reliable for measuring this effect. Why? Because at surface level, we can go very deep, and we can, not deep, sorry, we can go in a very small resolution. We can go up to nanometers. But if we go deeper into the part, we have the limit of the X-ray computer tomography that can go some, let's say, many microns, low millimeter, very maybe 2 or 3 millimeters, depending on the density of the part. So the area where we need to detect the defect, this is the red one, and currently we cannot detect them. So another alternative is detect defects via process monitoring. Okay, so in that case, we have a system that we have a monitoring of the process. We have two different sensors. One of them measures the radiation on the infrared level, somehow related with the melt pool, and other sensor that measures the wavelength, invisible wavelengths, so somehow related with the plasma formation, which leads on defects. And we obtain a measurement in less than 50 microseconds, which is good news at principle. But the bad news is that for each part, and not really big parts, we obtain files from 1 to 2 terabytes. So the amount of data is huge. This is an example of what we obtain for the IR sensor in one layer. So the idea is to test that methods in order to have a digital certification. With the monitoring data, be able to say that the part is good or not. So we have designed a test part with internal defects. We have measured them. It's easy. We know where we are. So, and those are the monitoring data, and we are implemented machine learning algorithms in order to obtain a map of probability of defects. So the blue areas are good areas, and the yellow areas are high probability of defect. So the algorithm is based on combining, filtering, clustering all the data, and the results show good. The results are very good. The probability of defect is defected, and the good news is that the measurements show that the defect areas where they are located. So in that case, it seems that we are in the good way. On the other hand, however, the detection is not deterministic. We have a probability, but we do not know exactly if there is a defect or not. And we cannot classify if the defect is lack of fusion or gas porosity. So we have we are far away from the solution, and we are only based on the IR sensor. So we have to implement new sensor, more data, and try to improve to obtain the deterministic solution of this is a defect and this part is not valid in order to certify it, because aerospace industry requires it, okay? And in the second case, this is for direct energy deposition. This process is very interesting for coating and repair high added value parts. The idea is to deposit material on previous parts, but here, one of the characteristics is that we have to make it good at the first time. We cannot test because we are repairing a specific part with a lot of high added value. For example, a blisk, which is 60,000 euros or dollars, and we cannot test. The part is what we have. So we have to make good at the first time. And there are a lot of parameters. So the idea is to develop a digital twins in order to set the parameters and also estimate which is the temperature, which are the residual stresses, and we are ongoing with that. Here you have some examples. This is the model for the powder and the gas flow. Then we have here the powder concentration. Even we can analyze the oxygen concentration or the volume fraction for the inert atmosphere in order to have or ensure that we are not oxidating the material. And here you can see an example of the digital twin application for a thermocouple embedding into a substrate. So here we have a thermocouple, and we are depositing material there in order to embed the thermocouple into the part. And here the challenge is not to destroy the thermocouple. So we have to melt just the coating of the thermocouple, sorry, and but not to go deeper. So the model helps us to obtain that set of parameters. Okay, so just two examples, and just to finish my presentation, I think that I'm time. We think that there is no discussion about the interest of metal additive manufacturing, and for sure metal additive manufacturing will be present now and in future for aerospace engines. Main applications will be, or will continue being, laser powder bed fusion for very complex parts and direct energy deposition for repair and coating. It's expected that the metal additive manufacturing will grow with the new programs. Those are the real opportunities of introducing new technologies in the aerospace sector when a new program or new engine appears. When the engine is set and start manufacturing, all is freezed, so there are no new implementation for this program. But with new engines, the forecast says that 30–40% of some parts for combustion chamber blades will be made by additive manufacturing. But on the other hand, it is necessary to continue developing techniques to make this technology reliable and to be in the same order as machining or forging or casting, where 100, even 1,000 years of history of knowledge of this process have to be taken more rapidly by the metal additive manufacturing. So thank you very much, and gracias, and feel free to ask ask me whatever.
Thank you very much. We're going to start our Q&A session. Anyone has a question for our guest today? Yes, Dr. Molina.
Sorry. You say that there is non-destructive testing already available, but then probably what you have to do is to do destructive testing, get the data, feedback into the model, and that will be the way to do it. And probably we have to do more mass additive manufacturing parts that are scale up, and then we do the destructive test and then go back to the, no? That will be the way to really build up a sense database.
That's it. For reasons of time, I didn't present, but our algorithm, the most data are obtained by destructive techniques, cutting the part. In that case, is where we see exactly which are the porosity, the size of the pores. So this is the manner to train our system, but at industrial level, we cannot destroy all the parts that we are making in order to see if they are good or not. So the basis, you're right, are based on destructive techniques, and they are needed. And in my opinion, we will continue destroying samples and some test parts for years. But the goal will be to have a non-destructive technique or a monitoring-based data or something that allows us to say that this process is going as we want.
Thank you very much, Dr. Alex. We have another question over there. Yeah.
Thank you for your presentation. We have already seen that there is a lot of numerical simulation have been used to model these new materials and so on. Based on the complexity of the problem, because it is a multi-scale problem, nonlinear problem, based on your experience, how reliable are computer simulations compared to experimental data?
Okay, excellent question. In my opinion, we are on the earliest stage of the simulation. And in our research group, it's a hot topic, the modeling. We started modeling in 2008 or something like that with a conventional thermal model. And now we are with the digital twin of the deposition process in collaboration with Siemens and the University of Munich. And we are going from the eldest the first thermal model. Now we are implementing thermal, mechanic, computer fluid dynamics, melt pool dynamics. So we are making the model very complex in order to have accurate results. We have to say that we are obtaining reasonable results, but for small parts, because the computational time is huge. So if we want to model a big part that could take hours in the machine, by now, for us, it's still very complex. And I'm talking about laser direct energy deposition. On the other hand, the powder bed fusion machine, there are some commercial models that works rather well, but I think that there are still far from the optimal solution. Comparison, for example, with sheet metal forming or casting, where the FEM models are in the industries and they are making business with that model. So this is my opinion.
Thank you very much. We have for one more over there. Yes.
Yep. Thank you very much for your presentation. I find it very interesting. Regarding the digital twin, my understanding is that an actual implementation of digital twin implies bidirectional update of the digital twin as a function of the manufacturing process. Now, if one has a digital twin that basically is unidirectional, which most of the finite element analysis simulations currently are, one is not really able to elucidate or highlight the issues that are happening actually. So the work that you're doing, does that develop tools and methods to incorporate the actual process data that's coming out of the process into the digital twin, and what do you think are the important things around that?
Mm-hmm. Okay, I think that I understand the question, but if not, please feel free to correct me. In our case, we consider the digital twin as a digital complete model of the process. So our goal is to introduce in the computer the same parameters that we are introducing in the machine, including not only laser power or feed rate or whatever, but including also the powder size, the cure of powder distribution, gas flows, whatever. And our idea is to obtain digitally the same picture that we will obtain in a real machine in order to save money. This is our strategy. Obviously, there are other strategies. For example, Siemens, another brand, is introducing process monitoring in order to make somehow a closed loop into a digital twin embedded in the machine with a much more easier model. In that case, the computational time has to be milliseconds, so the model is very easy. And they measure the process, some process parameters, not all of them, in order to adapt the process and adapt to new conditions, for example, in corners or if something happens. But this is another strategy. In our case, we are making a unidirectional digital twin. Yeah.